Okay, number 7 says if x plus y equals 3 and x squared plus y squared equals 8, then the product x times y equals what? In order to solve this problem, you've got to be familiar with how something like x plus y squared would expand if we went ahead and either applied binomial theorem, FOIL, or the box method, of course. So this would be equal to x squared plus 2xy plus y squared. That's also a very common factoring pattern called a perfect square trinomial. And we are given certain values. X squared plus y squared is 8, x plus y is 3. And we can go ahead and substitute in those values. For example, x plus y right here, we can replace that with 3. So on the left side we have 3 squared. Because of the commutative property of addition, it really doesn't matter what order we add all these terms in. So I could put x squared plus y squared way up front, and then add the 2xy at the end. The only reason I wanted to do that was because x squared plus y squared, I do know the value for that as well, so I can replace that immediately with 8. So now, let's evaluate the left. 3 squared was 9. Equals, and I can replace x squared plus y squared with 8, because it was given to me in the problem. It says 8. And then we have plus 2xy. If you notice, now we have an equation where we have nothing but numbers and then this value xy, and the value xy is exactly what we're looking for. So if you just use some basic algebra, let me rewrite this over here. 9 equals 8 plus 2 times xy. You would subtract 8 from both sides. That leaves you with 1 equals 2xy. Divide by 2 to solve for xy. And then you do get xy equals 1/2. 1/2 of the decimal is 0.5. So the answer is B. Number 8 is a very interesting problem. It says the equation x squared plus 4x plus k equals 0 has 2 imaginary roots. Which of the following is always a true statement about the value of k? So, in order for an equation to have imaginary roots, what that means is if you looked at a graph of this, it would never cross the x-axis. You would have no x-intercepts whatsoever. Let's look at the special case of if we simply had one solution, if we had one x-intercept. So imagine that this was a perfect square trinomial, similar to this pattern up here. X squared plus 4x plus 4 equals 0. That is a perfect square trinomial. We know that because we can factor this out as x plus 2 times x plus 2, or x plus 2 squared. That's equal to 0. And because we have something squared equals 0, we're going to have a single root. It's going to cross the x-axis at a single point. X plus 2 equals 0. So our root is going to be negative 2. And so that is a perfect square trinomial. And it actually looks a little bit something like this. It is a parabola, but it doesn't really cross the x-axis. It just kind of touches down on the x-axis once, at the point negative 2. We know that this parabola has to open upwards. We know that because it says the equation x squared. It's not a negative x squared, it's a positive x squared. So it's going to open upwards and it's going to have a root, or an x-intercept at negative 2. So if this graph were shifted up any units at all from this point, we would have 2 imaginary roots. The c value, when we're in standard form, ax squared plus bx plus c, the c value itself represents the y-intercept. So this does intersect the y-axis up here at 0, 4. Now, if we increased this number, if we took this number and we increased it at all, if we made it a 5, a 6, even something like 4.1, it would shift the graph up slightly, very slightly, because the y-intercept would change. And that would cause this parabola to shift upward like this. So from a graphing standpoint, what we notice is the value of k has to be greater than 4. It has to be greater than 4 for the graph to never cross the x-axis, meaning it has 2 imaginary roots. There's a more algebraic way to solve this problem, and that's by completing the square. So, if we have x squared plus 4x, and if you go ahead and move the k to the other side, you have a negative k, since that's how we normally set up problems for completing the square, we would find out that in order to make the left-hand side a perfect square trinomial, well, of course, we'd have to add this number 4 here. It's always half the middle term squared. X squared plus 4x. If we added a 4, we would have to add that 4 to the other side for balance. And then this can be expressed, again, as x plus 2 squared. That's still equal to negative k plus 4. Taking the square root of both sides, take the square root, you end up with x plus 2 equals positive or negative the square root of negative k plus 4. And you have minus 2 to go ahead and solve it for x. So in other words, x would be equal to the positive or negative, the square root of negative k plus 4 minus 2. Now the minus 2 is a real number. That's the real part of this. If we want this to have imaginary roots, we need this expression that's underneath the square root. We need that to be a negative, so we could set up an inequality. We could say, well, we need this negative k plus 4 value. We need that to be a negative number, so we need it to be less than 0. And so, rearranging this a bit, you can subtract 4 from both sides to get negative k is less than negative 4. And then when you divide by negative 1, the inequality sign does flip. So you get k is greater than 4. So that's more of an analytical way of thinking about this problem. But we get the same answer either way. K has to be greater than 4.